We're continuing in section 7.3, and we're considering series and parallel connections. And in this section we will be doing some calculations. As with other components, capacitors may be connected in series or in parallel. And here we have series capacitances. When connected in series, the total capacitance is less than the value of any of the individual capacitances. And so here we have CT for total capacitance, and we're going to see that it's 1 over the quantity of 1 over C1 plus 1 over C2 plus 1 over C3, and on and on. Now, this looks very similar to formulas we have used previously when we looked at resistance in parallel. This was 1 over R. When we looked at inductances, it was 1 over L. But this is capacitance, and this is not parallel. When we looked at resistance and inductance, it was in parallel. This is in series. So let's look at a circuit. Here we have a circuit with 3 1 microfarad capacitors, and the plate separation accounts for the difference in our calculations. Now, remember that when we said from our earlier simulations, we saw that as plate separation increased, capacitance actually decreased. Now, in a series circuit, we have the plate separation of this particular capacitor, but the circuit, as current attempts to move in this circuit, it doesn't only see that one, it sees this separation and it sees this separation. So it sees all 3 plate separations together. So that is going to result in a capacitance that's smaller than any of the 3. So if we did the calculation, let's bring up our calculator and let's do the calculation. So we would say, okay, 1 exponent minus 6, and that is effectively 1 microfarad, and we're going to say 1 over that value. And according to our formula, we're going to add all of them together, and since they're all the same value, we could just say times 3, and there we have the combined reciprocals of the 3 capacitances. And then to complete the formula, we needed to take the reciprocal of that value, so 1 over that. And here we come up with a value 333, but notice it is to the minus 9th, which is nano. And so let's note that value, 333.3 to the exponent minus 9. That is nanofarads. Now, that is going to be the equivalent of 0.333 exponent to the minus 6th, which is 1/3 of this value. So using our formula, we see that the capacitance that is experienced in this circuit is smaller than the smallest value. Okay, capacitors in parallel. When capacitors are connected in parallel, the total capacitance is equal to the sum of the individual capacitances. And so here we have a circuit connected in parallel, and this will be really simple since I have got them all the same size if you had them in different sizes, but you just simply add them up. Now, the reason that we're going to do this is that the plate area is effectively increased. Remember, in the simulation, as the plate area increased, the capacitance also increased. And so for purposes of current flowing in this circuit, it is seeing the plate area not of 1 capacitor, but of 3 capacitors. So the calculation in this case would just be 1 plus 1 plus 1, and the capacitance total would be 3 microfarads. Okay, series and parallel connections. Series capacitive reactance is the opposition to AC offered by a capacitor. And we talked about that in a previous discussion. Remember, this is measured in ohms. Capacitive reactance in a series circuit is found by summing the individual reactances. And so this is much like, remember, this is resistance, and so in a series circuit, if we have resistances, we just add them up. And so let's look at, we'll go back to this circuit again, and let's calculate the reactance of the individual first. So if we went in and we said, here we have this particular component, and what is its reactance? So we say 1 divided by, and let's use our bracket here, divided by the quantity of 2 times 3.14 times the frequency, which is 60 hertz, and then take that times the capacitance, which is 1 exponent minus 6, then we would end parentheses, equals, and we have about 2.65 K. So we would have 2.65 K, and remember that this is X of C, capacitive reactance, and this is measured in ohms. And so we would have the same here, 2.65 K and 2.65 K, and the total, what's the total? If we said this value times 3 equals about 7.962. So total 7.962 would be the total X of C, and this would be in ohms. Now, if you wanted to go into Workbench, you could do this and set this simulation up, and if you do that, you'll get, let's see, if you opened the circuit, let's say pretend we opened the circuit here, we insert a voltmeter, and if we this would be one way to confirm this, and we measured current, and if you do that in Workbench, the value you'll get is 1.257 milliamps, and the way you would confirm this is if you took 10 volts and you divided it by the current of 1.257 milliamps. Remember, voltage divided by current equals what? Resistance, and this is the value that you would get, and that could be a check to just to verify that this is in fact true. Okay, series and parallel connections. Parallel capacitive reactances are calculated according to the following, and again, this would be the same thing that you would do in a resistive circuit. And just remember, if this was an R, if you're calculating resistance, it'd be the same thing, and this would give you R. But we're calculating capacitive reactance. And so here we have capacitive reactance in parallel, and we had previously calculated the reactance of each of these components. We said that it was 2.65 K, and so 2.65 K, 2.65 K. And so again, if we brought up our calculator, we could say 2.65 and exponent 3, okay, that's 2.65 K, and we wanted to do 1 over that, and then according to, since all of these are the same value, we could take that times 3, and then again do the 1 over function, and our capacitive reactance would be 883 ohms, and that would be X of C, and that would be the resistance that this circuit would experience. Again, you could do the same thing we did in the you could insert a voltmeter in here in Workbench and calculate find the current, and then you could go voltage over this resistance, and that's the current that you should get. Circuit analysis of capacitive circuits. Once all of the capacitive reactance values are calculated for all capacitors in a given circuit, voltages and currents can be solved using the strategies presented earlier. And we did quite a bit of calculating with resistors in series and parallel. Once the reactances are calculated, then you can just use all those same formulas. Okay, this concludes section 7.3c.